And throughout this talk, I'm going to mention only one goal, which is to maximize the social welfare. The social welfare is the sum of the valuations of all the agents for the bundles that they get. Okay, so we have an allocation. Each agent gets some bundle of the items. And according to his own valuation function, he has some value for the bundle allocated to him, and we want to maximize the sum of the agent's valuation. This is called the social welfare objective function. So from an algorithmic point of view, it's very simple. We have an input, which is the valuation functions of the agents. And the algorithm gets these values as input and return as input some allocation, where the goal, again, is to maximize social welfare in polynomial time. Okay, remember, we are working here under computational constraints, so we want poly time. And it's known that in the most general form, for general valuation functions, this problem can be computationally hard, so we're also happy with approximately optimal social welfare. Okay, so we are willing to get approximately optimal social welfare. This is from an algorithmic point of view, and of course the question is, how well can you approximate the optimal social welfare if you have only polynomial time to do the computation? And now we are getting to the economic perspective. So now we have a mechanism. The mechanism gets some input valuation functions of the agents. And we also want to approximately maximize the social welfare in poly time. But we also want to satisfy some additional economic properties. And for now, I'm talking about it in a very abstract way. It's not necessarily, Kostis talked in the morning about incentive compatibility. We want agents to be truthful. It's not necessarily the only economic property we can think about. We can think about other settings where this is not our desired property. So here it's very abstract. We have some economic property that we want to satisfy. And in order to achieve this economic property, we are granting the designer of the mechanism an additional power in the form of payments. So in addition to deciding what items go to what agents, the designer also says how much each one of the agent pays. And this goes back to the second price auction example. So if you have to compute the max and you want to be, for example, incentive compatible, if you're not charging agents, you cannot do it. But if you're charging agents, you can do it. So this is one example of economic property that can be achieved via a mechanism. And now the holy grail in the meeting point of algorithms and economics is to get the economic property for free. So we already know that we get some approximation because of the computational constraints, but we don't want to have additional loss incurred due to the economic property. So the holy grail, if you wish, is for every approximation algorithm, we want the mechanism to approximately preserve the social welfare that the algorithm gives us, and at the same time also to satisfy the desired economic property. And it would be really nice if this will be done through this black box reduction, which decouples the algorithmic work from the economic work. Now, as I said in the beginning, for the purpose of this talk, I'm not happy with just any mechanism. So if you see here, I say that the designer can set up payments for the agents, and there are no constraints about these payments. They can take very complex forms, arbitrary forms. They don't need to correspond to any structure of item prices, for example. And in this talk, I want to concentrate on a very specific type of mechanism which works by posting prices to items and selling them. So in posted price mechanisms, we have a vector of prices for each item. So this orange costs P1, strawberry P2, et cetera, et cetera. And now an additional thing you need to know is that once we have an allocation, so say agent 1 gets the first and second items, his payment is just the sum of payments of the items, P1 plus P2. So the utility of an agent under an allocation xi and a payment vector p, a price vector p, is his value for the bundle he gets minus the sum of payments of the items in his bundle. Okay, any questions so far about the model? Good. Okay, so as I said, we will talk about two very different scenarios. The scenarios will be different in the informational model, we assume. One will be full information setting, the other will be private or Bayesian setting. And in one of the scenarios, the posted prices will be inherent in the solution concept. In the other, we will require the mechanism to impose posted prices, etc. So let's start with the first scenario. In the first scenario, the desired economic property is conflict-free outcomes. And I'll define, and I'll say what I mean by conflict-free outcomes. So we have the input, and this is full information. The designer of the mechanism here knows exactly the valuations of the agents. And this conflict-freeness notion relates very closely to the notion of a Walrasian equilibrium. What is a Walrasian equilibrium? So first of all, what is an outcome? An outcome is an allocation, a vector of allocation, and a vector of item prices. And we say that an outcome is a Walrasian equilibrium if each buyer, for every buyer I, the allocation that he gets in this outcome maximizes his utility, given the prices. An outcome is composed of both an allocation and prices. So every agent comes to the market, he sees the item prices, each one has his own most preferred bundle, and each one of them get his most preferred bundle. There is no overlap, no competition, and all the items are sold. This is called the Walrasian equilibrium. This is a really nice notion. As we can see, it's very simple, just item prices. It's fair. It has very strong fairness properties. Not only that there is no agent who would like to switch with one other agent, each agent gets really the bundle that he prefers the most out of all the items in the market. And the first welfare theorem tells us also that every Walrasian equilibrium truly maximizes social welfare. Not approximately, but truly maximizes social welfare. So this is really nice. However, there is also a dark side to a Walrasian equilibrium, which is that existence is extremely restricted. In most cases, a Walrasian equilibrium simply does not exist. For example, here is a very simple example. We have Alice. Alice wants to have her bicycle fixed, and we have Bob who has unicycle. So Alice wants 2 wheels, and she values the bike at 4. So her value for both wheels is 4, whereas she doesn't value any, her value for any single wheel is just 0. In contrast, Bob only needs 1 wheel, so he values every single wheel at 3, but also the pair at 3, because he only needs 1 wheel. So it's very easy to see here that a Walrasian equilibrium doesn't exist. Why? If there is a Walrasian equilibrium, by the first welfare theorem, we know it should maximize social welfare. So it should give both wheels to Alice. However, in order for every agent to get his most preferred bundle, every wheel needs to be priced at least 3. Otherwise, Bob wants it. But if both wheels cost 3, then Alice don't want them. So there is no Walrasian equilibrium, even in this very simple example. And in fact, it is known that a Walrasian equilibrium is guaranteed to exist only for a very, very restricted class of valuations called gross substitute. So this is the class gross substitute. It's really tiny. And we have the whole spectrum of valuations which we don't have existence for sure. So this is really bad. And the motivating question is whether we have a way to extend the theory of Walrasian equilibrium to combinatorial markets with general valuations. So we want to preserve the nice notions, the nice properties of a Walrasian equilibrium. We don't want to lose the simplicity, the fairness, but we want it to hold in general. We want it to exist in general. And the answer that I would like to show you here is that we can do it, and we can do it through bundles. So what's the notion of bundles? So here is the market. The market has 3 goods. And the only thing that is different from the previous scenario is that the seller can pre-package some of the items prior to sale. So for example, the seller can say, no more strawberry and banana, now I sell the bundle. I'll sell them together for $7, and I sell the orange for $3. So now an outcome is composed of, in addition to allocation and prices, it is also composed of a partition of the items into bundles. And then once we have a partition, we need to decide about an allocation, what bundle go to what agent, and what are the prices of the bundle. And we say that an outcome is conflict-free if every buyer receives her most preferred bundle in this reduced market, given the bundles and prices. So now it's very easy to see that existence is for free. We always, such a conflict-free outcome always exists, because in particular, we can just bundle everything, all the items together. And the big question is, what about social welfare? Can we recover a high social welfare in a conflict-free outcome? So let's revisit the wheel example. In this wheel example, we said before there is no well-raised equilibrium. There is no way to price the individual items such that we get a well-raised equilibrium. But what can we do if we can bundle? One option, yeah, we can bundle, very good. We can bundle the two wheels together and price them at 4, thank you. And then we can achieve optimum, right? We give Alice 2 wheels, she's very happy. Bob certainly doesn't want the bundle of the 2 wheels for $4, and we recover the optimal solution in a conflict-free manner. So now we have 2 theorems, one existential and one computational. So first of all, we show that every valuation profile, so remember the motivation was to extend this theory of well-raised equilibrium to general valuations. So we show that every valuation profile, as complex as can be, always admits a conflict-free outcome that preserves at least half of the optimal social welfare. And in terms of computation, we show that this conflict-freeness essentially comes for free. In what sense? For every valuation profile, given a black box access to some algorithm A that computes for us some allocation, we can compute in polynomial time a conflict-free outcome that gives us at least half of the social welfare of that algorithm. Okay, so whatever, in other words, whatever approximation you can get to the social welfare problem in any algorithm, you can preserve at least half of this social welfare in a conflict-free manner. Okay, and this is through posted prices, right? We bundle, then we post prices on the bundles, and then agents come to the market and purchase their most preferred bundles. Good. Okay, so this was the first scenario. And now I would like to switch gears to the second scenario, which is more closely related to the stuff Kostis talked about in the morning. So now I go back to the desired economic property that I'll talk about now is incentive compatibility. So as before, we have this mechanism. The input, we have agents in the market with valuations, but now the input is not the valuations because we don't know them. The valuations are private to the agents, but each valuation submits bids to the mechanism, and we assume that agents submit their bids in a strategic way. And we want our mechanism to have the property that it is incentive compatible, meaning that for every agent, it is in his best interest to truthfully reveal his values. Okay, so essentially there is no difference between the vector of values and the vector of bids. Then we say that it's incentive compatible. And I'm going to focus on submodular valuations. Submodular valuations just means that we have decreasing marginal contribution, decreasing marginal valuation, meaning that if we have a set T that is a subset of some larger set S, the marginal valuation that we get when we add J to T is greater than the marginal valuation that we get when we add J to S. Okay, as a side note, I would like to mention that these results really hold for a larger class of valuations called XOS, but I don't want to get into it. This is, I think, a very intuitive class of valuation, so let's stick with this. What's known about just the algorithmic problem? So we know that we have a constant factor approximation that we can get in a polytime for welfare maximization under submodular valuations. In terms of incentive compatibility, we have some, so essentially we have a gap. Why? So I don't want to get into the exact definition of the computational model, but we can talk about two different computational models. One is value queries, and the second is demand queries. Demand queries are stronger, so positive results with demand queries are weaker. And what we know is that any subpolynomial approximation requires an exponential number of value queries. If we want really value queries, we can't get subpoly approximation. And under demand queries, we can get essentially a logarithmic approximation. But realize that we have a gap here, because from the algorithmic perspective, we can get constant approximation. When we want to impose this economic property of incentive compatibility, we have a log approximation. So the major open problem, which is, by the way, still open, is whether there is a polytime incentive compatible mechanism that achieves constant factor approximation for submodular valuations under demand oracles. Okay, in other words, do we have a gap between the algorithmic problem and the economic problem? Is incentive compatibility, is it coming for free for submodular valuations? And in the context of this talk, I want to make my life even harder and ask whether I can do it not just with any mechanism, but with this posted price mechanism, this very simple mechanism that simply posts prices on the items and let the agent choose their most preferred bundles. Okay, so we don't quite answer this question, but we do answer it in a Bayesian setting, independently. Okay, so what is this Bayesian setting that we are dealing with? Each valuation, so before I talked about this private information, each agent has his own valuation function, VI, which is known to him, and the designer has no information and no access to this valuation. Now we relax this assumption a bit, and we say that each VI is drawn independently from a known distribution Fi over submodular valuations, and the designer knows these FIs. He knows the distributions of every bidder. And we ask, can we design a polytime mechanism which works via posted prices that achieves a constant approximation for submodular valuations? Two remarks. One is that we really want to impose here, when we say polytime, we want truly polytime, and this is in contrast to sometimes when we move to talk about Bayesian settings, we only ask for polynomial time in the size of the support of the distributions, which can be really large, and in our case, we really want polytime, not polytime in the size of the distribution. And the second remark that I want to make is that we do want to impose dominant strategy incentive compatibility, and this is in contrast to Bayesian incentive compatibility that Kostis presented to us before.
What is your input? What do you mean by truly polytime? What is the input? It's not the support of the...
Okay, so you have sample access to the distributions. I'll get to it. Okay, so I want, so remember in Kostis' talk before, he also had a Bayesian setting, and he used the notion of Bayesian incentive compatibility, which means that every agent, it's in the best interest of every agent to act as we want, given that other agents also act as we want. Here we use the stronger solution concept of dominant strategy incentive compatibility. So the input is coming from distributions, but we want each agent to act as we want in a dominant strategy. No matter how other agents behave, I want this agent to be truthful. Okay, I would like to mention that posted price mechanisms have been extensively studied for revenue maximization. Here I'm talking about social welfare maximization. And in these works for revenue maximization, the motivation for using posted price mechanisms was because of their simplicity. we have some very, very complex optimal mechanisms, which we know to describe, but they're very complex. And the question is, can you get approximately good outcome with very, very simple mechanisms which work by just posting prices on items? And I want to mention that our posted price mechanism is even simpler than those studied for revenue maximization. So with this introduction, let me describe you what I mean, what is the form of our posted price mechanism. So first of all, we have agents, and the agents have their distributions. The designer picks a price vector, just one price per item, just like before. And to your question, Yuval, those prices are computed based on these distributions with sample access to these distributions. So the designer has sample access to these distributions. Based on those distributions, he posts some prices to the items. Then an arbitrary arrival order pi is determined on the agents. So let's say we have agent 3, then 1, then 2. Then bidder values are realized. Each agent can observe his own value. They come to the market according to the order pi, and each agent chooses his most preferred bundle given these prices among the remaining items. Okay, so for example, Alice comes first to the market. She sees those prices. She says, oh, under these prices, my most preferred bundle is the orange and the strawberry. She gets them. Then the second agent comes to the market. She sees the bananas for $7. She doesn't want bananas for $7. So then Bob comes to the market. He wants bananas for $7, and that's it. That's the mechanism. Very simple. Posted prices, agents come sequentially and purchase their most preferred bundles. And what we show is that for distributions over submodular valuations, there always exists a price vector that gives us, in expectation, social welfare that is at least a half of the expected optimal social welfare. Okay, so there exist such prices in terms of existence. And then we also show computationally that if we have a black box access to a social welfare algorithm A and sample access to distributions Fi, which are submodular, then we can compute, now even just with value queries, prices in polynomial time such that the expected social welfare is at least a half of the expected social welfare of the algorithm A minus epsilon. Okay? And as a corollary, we get a dominant strategy incentive compatible, constant approximation, poly time, posted price mechanism for Bayesian submodular valuations. So I'm done. For summary, so all I have to say is that I hope I advertised posted price mechanisms good enough to show you that they are very simple and natural. They're really not, in general, we can talk about very complex mechanisms, but there is a lot of criticism, even in the theory community, about these complex mechanisms, and there is a very huge trend now to move to simpler mechanisms, even if they come at some loss. And here I show that those posted price mechanisms can achieve high social welfare in various economic scenarios. The first was type of a Walrasian equilibrium, conflict-free outcome in a full information setting. And for every approximation that we could get for social welfare, we can get at least a half in these conflict-free outcomes using posted prices. And in the second scenarios, we talked about Bayesian setting, where it's private information, private valuation that are drawn from known distributions. And what we saw is that we can design posted price mechanisms that, given access to some approximation algorithm, we can get at least a half in expectation of the social welfare that can be obtained by this algorithm. Thank you.